Start. Loudly.
Good morning everyone. My name is Atharv. I'm from group 7 and I will be giving the introduction about quantum kernels in focus, which is a theoretical and simulated investigation of quantum support vector machines. The overview about the problem and hypothesis. The classical problem. The support vector machine SPM is a powerful classifier where its power comes from the kernel. The kernel linear Arya polynomial maps data to a higher dimensional space to find a non-linear model. Choosing the right kernel is often a process of trial and error. The quantum hypothesis. Can we use the principles of quantum mechanics to create a more powerful and systematic kernel? A quantum computer's Hilbert space is exponentially large. M Hilbert is equal to 2 large. By encoding data into this vast space, it can actually find problems that classical methods miss.
Sign up.
Quiet, everybody please be quiet. Loudly.
The mathematical function that efficiently computes the dot product of data into high-dimensional space, feature space, without explicitly creating those vectors. Like you can see the formula x1 and xi and xj. It creates the dot product which gives the component of xi and xj. It maps the similarities between the two data classes. And now we come to the quantum kernel. It is a quantum circuit that encodes classical data into a quantum state. Like there are data sets which it encodes or converts it into quantum states. And this kernel is then measured measures the similarity between the quantum states and tries to find the similarity, and also this is used for the classification of data. So our benchmark, the classical kernels is our benchmark. Quantum kernel is a pretty new topic. The classical kernel is used to see the efficiency and what and how much progress this quantum kernel field has. So in the classical kernel, there are two types which will be our focus. One is linear kernel, which performs no feature transformation. It simply tries to find a statement. Like there is these are two data sets for visual graphics and so these are two data sets. One will be of blue color, one will be of red color. The linear one will just try to draw a line and will try to separate it. After that, the next one is RMS kernel. RMS kernel tries to convert the data sets into many dimensions. Like it's not limited to one such plane. It can convert it into 2D or 3D or 4D or 10D. So yes, this is the photo of the RMS kernel. This is what it is showing in the 2D space. But the RMS kernel works like this. This is one data set. This is another data set. It tries to create one vector plane between this blue one and red one. This is the work of RMS kernels. And I try to classify based on that.
Whenever you are speaking, loudly say your name.
My name is Nithin. My number is 25BC561. I'm going to explain the quantum feature part. So the way I encode data as qubits. So we take a Hilbert space, which is a qubit system as we said. So for example, if there are 4 features in every 4 qubits, which is 16, which will give us 16 dimension size. The Harman gate, we use the Harman gate to base position because it puts qubits in a state of and market. With this state, we use rotation gate, which will create like an entire event. We add xenon gate as well, which will create complex Z feature map and the ZZ feature map. We use the Z feature map for non-entangling, which is basically the classical linear kernel. In the Z feature map, which is encoded independently, it cannot capture correlation between features. It has limited expressive power and it treats each feature separately. This is why it is a classical kernel. In the ZZ feature map, this is used for common problems like the parity problem which we will see in the next slide. This map has an entangling layer, which is why it is not used classical linear kernel or classical data. It is used for common data. So this feature map has complex correlations as compared to the Z feature map, which just has limited power. So as you can see in the diagram, we start with the 0 okay, and then we have an RMS gate which stays slow position, and then we have the P gate represents the rotation around the x-axis. Z axis. So as it rotates, this will be equal to the Z feature map. The second gate here will create the ZZ feature map. This creates a superposition state, and this will create the entanglement state. The same circuit here is replaced here again because there are multiple layers in this circuit. Multiple layers are used because you can create you can increase the expressiveness and get data be more accurate.
Myself, Vaishnavi, for C5 Since we all know that the fully escape doesn't exist, so we use a hybrid pipeline which combines both classical optimizer and quantum coprocessor. In the classical optimizer, we use a built-in thing called CPQM, which is responsible for the escape optimization, but it needs entire kernel matrix to compute kernel values, but it can't directly compute it, so it has a quantum computer to do it. Coming to the quantum coprocessor, which is using the method. The only job is to coprocessor that calculates the kernel value. It uses a special circuit called commute, which is used to know the similarity of data points. The probability of measuring n of 0 gates directly gives the kernel value, which it returns to the classical range. The results show the different kernel values of various inputs. The entangling ZZ map achieves performance parity with the best classical RPF kernel. The non-entangling Z map, like a simple linear kernel, as we predict.
Good morning, everyone. My name is Vishnu. I'm going to talk about the topic, the parity problem. So let's get into it. What is the parity problem? The parity problem is a synthetic data set designed to be hard for classical kernels. Data points labels based on parity, even or odd, of the sum of its bits. It's represented by the formula y is equal to sigma xi into mod 2. Okay. So why does the RBS fail? That's due to the parity problem. The RBS kernel's logic is that nearby points are similar to each other, while the parity disproves this assumption. So let's get better clarity by looking at an example. Let's take this point 0, 0, 0, 0, and it has a label of 0. Let's take another point 1, 0, 0, 0. We would assume this would, since these are nearby points to each other, according to the RBS kernel's logic, and they are close to each other with only a distance of 1, they would have the same label. But in reality, that is not true. Due to parity, the 1, 0, 0, 0 point has a label of 1, which is opposite to the other nearby point. Since these have opposite labels, this creates a checkerboard pattern that confuses the RBS kernel. We have an image of the checkerboard pattern for better clarity. Next is the results, the quantum advantage on parity. So we got 4 test cases. We got the classical, which is classical linear, classical RBF, and a non-entangling kernel, which is the VMA. And all of these have completely failed. Note, I'm saying completely failed, even though there's 50% accuracy on the board, but these are just random guessing. Okay, so next we have the entangling ZZ map, which has achieved perfect accuracy. This has demonstrated a clear quantum-like effect. Next.
Hi everyone, I'm Hasini Chowdhary. I'm here to explain why the RMS map solves the parity problem. To solve the parity problem, we need to capture the interaction and not the individual values. The classical RBF map fails to do this because it has an assumption made that two closely based kernels have same label, but this is not the case. Extremely closely based values can have the different labels. And also RBF depends on smoothness, but parity is the smoothness. And the second map, the Z map logic. This also fails here because every input that it receives is received as a separate unrelated value. This completely defeats the process of wanting to solve a parity problem because we don't need a separate unrelated problems. We need the interaction between them. And now we come up to the ZZ map logic. This perfectly solves the problem that the parity is looking for because this creates an entanglement between the inputs that it receives. So we have demonstrated how the quantum support vector system works and also provided a clear example of the quantum advantage. Some of our future works is to explain how the quantum support system works and to solve the parity problem on a real-time quantum system and to see if the advantage persists and also to create a more complex feature map.
This is the iris data set, right? It has four features, four data, which will be classified by both quantum and classical data. Okay.
Like the pattern like the now.
Yes. This test split will
Usually like people who just go to the ones like where the comparison or the accuracy. This is like the classical one, accuracy is more than the quantum one now. So this is like 90, I guess 96.67% is the classical, right? If quantum is going to be less.
Yes, for
Rational is actually entangled. Entangled it will be almost same. I cannot still say this is better than the classical, right?
for this data set, it is like this iris
Even
data
for
set
the
is-
next data set, that is more 100%.
Yes, for like parity one is totally in favor of research attack. It is like built for QSP. The classical and linear one is same.
What is the
It is parity.
First, good morning. Sir, today you will also something from
This is our simulation.
why you are running this?
It is HTML file.
Huh?
I created an HTML file and CSS.
Running in this local system or in the cloud? In local system.
So this is the iris data set. This is the test. 30% will be used for testing the data. 70% will be used for training the data in the USB and classical USB. That is like the repetition. How many times will run the kernels to get the accuracy. So we get the percentage. In this, like we will put that quantum one is slightly underperforming than the classical one. You see that in data set, the classical ones are are very